This is lab 4, circuits, and I'm on Janire. So the purpose of this lab is to use principles of charge conservation and current conservation to calculate conventional current values in a circuit. We also want to utilize multimeters to obtain values of conventional current and potential difference. Lastly, we want to observe the behavior of resistors and capacitors in a circuit. In a preview of the results, we want to compare the predicted and measured values of conventional current in a circuit with resistors in the series, which was 0.02 amps for both, and then we want to measure the time it takes for a capacitor to charge and discharge. We also want to compare the experimental value to a calculated value obtained from a differential equation relating potential difference and the time constant, or RC, which was 6 seconds. Some physics principles used in this lab were the Kirchhoff node rule, which is the conservation of charge, stating that the current in is going to be the current out, and then the Kirchhoff loop rule, which is the round-trip potential difference is going to equal 0, so delta V is going to equal 0. The delta V of the resistor is I times R, where I is current and R is resistance, and then delta V of the capacitor is Q over C, where Q is charge and C is capacitance. So for the RC circuits, capacitors charging and discharging, and then the time constant is the time at which the voltage difference has dropped to 1 over E of its original value, which is a rough estimate of how long it takes to charge or discharge the capacitor. And the initial conditions for this experiment were shown on the left. And then I calculated the current accordingly, and I used the node rule where I1 equals I2, and then the loop rule where the sum of all the potential differences is going to equal to 0 since it's a loop. Going counterclockwise, it's going to be 2 EMF, and then the delta V's are going to be negative. And then I plugged those values into the node rule and got this equation, and then I plugged in the values that were given to get 0.0204 amps for the current of both. And doing the experiment, the prediction was the same as the model. It was also 0.02 amps, and then when the ammeter connection was reversed, the value was negative. Here, the ammeter read 0 amps, and then the voltmeter read 3, and with an open circuit, there was no current, and the potential difference across the opening is the same across the batteries. Here, here I plotted all of these, and then the loop rule is going to be delta V equals 0, so ultimately all of these are going to have to add up to be 0, and they do. Here I calculated the resistance values for all of them, and got 48 ohms, 102 ohms, 0, and 0 accordingly. And then after attaching the voltmeter, the ammeter didn't change because the resistance of the voltmeter is so high that no current flows through it, and the conventional current is basically left unaffected. And then adding an ammeter in parallel to one resistor current, the current increases because it's going to branch off to the ammeter, and the ammeter has no resistance. And so the current will be higher than if all of it went through the resistor. So for the RC circuits, the charge is going to be 5.5 seconds for 10 ohms, and I got 10.1 for the 20 ohm bulb. And then for discharge, I got 4.9 for the 10 ohm, and then 9.6 for the 20 ohm. So it was approximately twice as much for double the ohms. And then as a capacitor charged, the light turns on and it dimmed as time passes, and I decreases and reaches 0. And then same thing as the capacitor discharges, light turned on and then dimmed as time passes, and I decreases and also reaches 0. Here I plotted all of my values, and then added a best fit line, and my equation was negative 0.165x minus 0.0179. And the slope is negative, and then using those values and plugging that into the equation, I got my RC value to be 6.06 seconds. And then comparing that to the computed value of RC, I also got 6 seconds, so they ended up being the same value. And in conclusion, series and parallel circuits follow the Kirchhoff loop and node rules, and the current and potential difference values aligned. The RC circuits are time dependent, and the light bulb dims as capacitor charges and discharges, and the time constant can be found by plotting potential difference versus time, as well as calculating RC. And some errors that we could have encountered in this lab are that imperfect potential difference readings when collecting at each second for the graph. And then what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? A real-life ammeter would have provided some resistance to the circuit, so the current reading would have been lower than on the simulated ammeter. And what if we used a real battery to charge a real capacitor with no resistor? The capacitor would charge up much faster in the simulated model than the real life model, because in real life, the wires would have contributed some resistance.